Hey, how's it, guys? Welcome back to my channel. Science is often misunderstood as a collection of fixed conclusions. The earth is round, gravity exists, evolution is true, the universe began with a big bang. But science itself is not those conclusions. Science is the method, a process, a discipline of observation, testing, prediction, correction, and skepticism. Its strength does not come from claiming certainty, its strength comes from allowing itself to be wrong. Because once science is treated as a rigid authority rather than a method of inquiry, it stops behaving scientifically. The phrase trust the science becomes dangerous when it implies conclusions that are beyond the question. Genuine science has never feared questioning. In fact, questioning is the engine that drives it forward. The history of science is not a story of perfect people arriving at eternal truths. It is the story of imperfect humans repeatedly confronting reality and reality correcting them. Reality has a stubborn streak. Science is a structured method for investigating reality. Through observation, measurement, hypothesis formation, testing, repetition, peer scrutiny, predictive capabilities, revision when evidence changes. Science is not what explanation feels emotionally satisfying, what explanation protects tradition, what explanation protects authority. At its core, science asks what explanation best matches observable reality. Scientific conclusions are always provisional. Even extremely well supported models remain open to refinement and adjustments. This is not a weakness, this is intellectual honesty. The foundation is observation. Long before advanced mathematics, satellites, or labs, humans observed nature. They observed the changing position of the stars, lunar phases, lunar eclipses, planetary motion, seasonal cycles, ocean tides, shadows changing with latitude, the curvature of Earth's shadow during the lunar eclipses. Our ancestors observed all of these things. Science begins not with belief or ideology, but with the observation itself. A critical scientific principle is distinguishing what is observed from how the observation is interpreted. For example, you see ships disappear hull first over the horizon. This suggests curvature. The alternative interpretations may be proposed, but they must explain all observable details equally well or better. This is where many debates fail. People often confuse disagreement with refutation. Proposing an alternative explanation is not enough. A valid scientific alternative must match observations, predict future observations, remain internally consistent, survive testing, and explain more than the existing model. The burden is not merely to doubt. The burden is to explain reality more successfully. Science evolves because new evidence emerges. Examples include the geocentric model, when humans once believed Earth was the center of the cosmos. This model survived for centuries because it matched everyday experience. But increasingly precise observations revealed inconsistencies. The heliocentric model better explained planetary motion with fewer contradictions. And then science's understanding changed. Another great example is Newtonian gravity. Isaac Newton's equations accurately predicted planetary motion and remains extraordinarily useful. But later observations revealed tiny discrepancies. Newton was not completely wrong. His model was just incomplete. Science advanced not by destroying previous knowledge, but by improving the understanding of it. Scientific progress depends on skepticism. Without opposition, errors persist, assumptions calcify, and institutions become dogmatic. Many major scientific breakthroughs began as minority positions. Examples include germ theory, continental drift, meteorites originating from space, the existence of deep time, and quantum mechanics. Unhealthy denial will ask, what evidence can I ignore to preserve my current position? Healthy scientific skepticism asks, does the evidence support the observations? To understand scientific debate properly, we must examine methods used both constructively and destructively. Constructive scientific skepticism includes independent replication, demanding measurement accuracy, identifying assumptions, testing edge cases, re examining old conclusions, and looking for falsifiability. Destructive skepticism often includes using isolated anomalies while ignoring the larger body of evidence, rejecting every answer while demanding impossible certainty, replacing evidence based explanations with claims requiring vast hidden coordination, misunderstanding scale or perspective in astronomy and physics discussions, confusing personal intuition with physical reality. The universe routinely behaves in ways human instincts did not evolve to grasp. A case study: the shape of the earth debates. Few topics demonstrate the distinction between method and conclusion better than the debate surrounding our Earth's geometry. Scientific understanding of Earth's shape did not emerge because institutions declared it. It emerged because multiple independent observations converged, different stars visible at different latitudes, changing angle of Polaris with latitude, Earth's circular shadow during lunar eclipses, time zones, great circle navigation, satellite communications, planetary observations, gravity measurements, horizon behavior, long distance photography, and orbital mechanics. Most importantly, no single observation alone proves the model. Science rarely works on one concept alone. Instead, confidence grows when many independent lines of evidence align consistently. This convergence is one of science's strongest tools. When observations contradict a preferred worldview, conspiracy explanations often emerge. But scientifically, conspiracy claims create larger problems than they solve. For example, to reject modern astronomy entirely would require coordinated deception among amateur astronomers, universities, navigation systems, space agencies, telecommunications engineers, pilots, and independent observers worldwide. Such a conspiracy would require impossible long term consistency across cultures, nations, enemies, and generations. Science prefers explanations requiring the fewest unsupported assumptions, and this principle is known as parsimony or Occam's razor. One of science's greatest strengths is repeatability. You do not need to trust authority blindly. You can test many claims for yourself. You can observe the moon phases, planetary motion, star rotation, seasonal constellations, pendulum motion, atmospheric refraction, eclipse timing, angular measurements. The scientific method empowers ordinary people. That democratization of observation is one reason science became so powerful. Science does not claim omniscience. There remain profound unanswered questions. What caused cosmic inflation? What is dark matter? What is consciousness? Are there limits to space-time? How common is life elsewhere? Acknowledging uncertainty is not weakness. What is weakness is pretending certainty where none exists. Great science says, here is the current best explanation based on the available evidence, not questioning is forbidden. Humans naturally seek certainty, identity, and belonging. Sometimes beliefs become emotionally protective rather than evidence based. This affects everyone, including the scientists. That is why scientific methodology matters more than individual personalities and egos. The method acts as a corrective system against our biases. Not perfectly, but better than intuition alone. Scientific models are maps, representations of reality, not reality itself. A map can be improved over time without disturbing the previous information. Even incomplete models can remain enormously effective. A model repeatedly producing accurate predictions earns confidence, not because authority declared it true, but because reality repeatedly agrees with itself. Science is not and will not be a sacred institution. It is a disciplined method for reducing error, a method built on observation, testing, skepticism, replication, revision, and intellectual humility. Its conclusions are always open to challenge, but challenges must meet the same standards demanded of science itself: evidence, consistency, predictive power, and explanatory strength. The goal of science is not to defend belief. The goal is to align understanding with reality as honestly as possible. And reality, no matter what humans believe about it, continues to reveal itself to those willing to observe carefully enough. Because reality retains veto power. So, guys, thank you so much for watching. Please stay safe, and I will catch you in the next video. Bye.